Okay, welcome to section 1.3, functions and their graphs. So in this section, we're going to be taking a look at functions. What is a function? How do functions work? All that kind of business. And we're also going to be taking a look at graphing functions. Okay. So what does this mean? Well, first off, what's a function? Okay, so our objectives are to use function notation and to evaluate a function, to find the domain and the range of a function, sketch a graph of the function, identify different types of transformation of functions, and to classify functions according and recognize when a function is actually a combination of other functions. But what you'll notice is in every single one of these definitions is the word, objectives, is the word function. So what is a function? Well, here is the book definition of a function, and it reads, a relation between two sets, x and y, is a set of ordered pairs, each with the form lowercase x, lowercase y, written as an ordered pair with parentheses around it and all that. Right, so written as an ordered pair, where x is the member of the set x and y is a member of the set y. Now, if you've never taken any set logic courses before or done any set notation, done much with set notation, we want to talk about some notation here real quick. You'll notice that these two are capital letters, whereas these two are lowercase letters. The capital letter represents the set. The lowercase represents an element or a member of the set. So to say that you have a relation between two sets means that you have some sort of rule that you follow that takes an x and pairs it up with a y. It takes an element of the first set and pairs it up with an element of the second set. Now that's the definition of a relation. A function is a special kind of relation. So a function from x to y is a relation between x and y that has the property that any two ordered pairs with the same x also have the same y. Okay? Any two numbers that have the same x also have the same y. So what this means, if I can just give you a real simple, quick example. Suppose that I told you that x was the set 1, 2, 3, ... ellipsis goes on forever and ever and ever and ever. And I told you then that y was the set 2, 4, 6, ... And then I could say that ordered pairs are always of the form n to n. And that would be a relation, more specifically, that would be a function that takes a member of x and pairs it up with a member of y. And then what does that notation mean? Well, it means that the number 1 gets paired up with the number 2. And the number 2 gets paired up with the number 4. And the number 3 gets paired up with the number 6, and so on and so forth. And so what makes this a function? Well, it says if you have two ordered pairs and they have the same x, what will they also have? The same y. So if 7 goes to 14, and I start at 7 again, where do I have to go? Well, I have to go to 14. Okay. Now, in this way, in this notation here, this x, y ordered pairs, we say that the variable x, the first represented variable in that, is the independent variable, and y is the dependent variable. Y depends upon x. X can be anything. The first number from the first set can be anything, but y depends on what that x was. And so that's how that works. So what you should be looking for here is that we need you to be comfortable with the word function and what does a function mean. Okay? All right, so not that, this. This is the definition, okay? But it adds some more interesting notation. So this first set right here basically just restates what we said. X and y are sets of real numbers. A real value function f is a real variable of a real variable x from x to y as it corresponds assigns to each number x in x exactly one number y in y. So x and y are sets of real numbers. A real valued function on the variable x from the set x to the set y is a corresponds that assigns each number x in x exactly one number y in y. The domain is the set x, right? the number y is the image, there's another term for you, of x under f, and is denoted by f of x, which is also called the value of f at x, and the range is the subset of y consisting of all images of numbers in x. Say, wait, what? So here's a picture. I was trying to do it, but let's give this let's give it a real simple example. I'm going to go back to the example I used before. All right, so let's say that x is all real numbers, and let's say that y is also all real numbers. Okay, and let's say that the function f of x is going to be the set, I don't know, how about 2x, just to keep things simple. It's basically redoing what we did up here, but now instead of with just some numbers, we're using all the numbers, real numbers. Okay, so what does this language tell me? What is it supposed to be telling me? Okay, well, I've got a set here, which is my domain. It's the set where things start. It's my values that I can choose to use to put into my function. I've got a set here, which is where these things are going to get mapped onto. Okay? And then I've got a rule here that tells me how to do this mapping. Okay? Now, I would be amiss, I would be wrong to say that this entire set is the range, because it doesn't have to be. We could miss some numbers and that would be okay. Now in this example that I have here, the range is the complete set y, because you can find any real number and find the x that would get you to it. But there are other functions out there that when you map them over are going to miss some numbers. What if I change my function down here? What if I went in here and I said, I want to make this be a different function. I want to make this be the absolute value of x. Now what's going to happen is there are going to be a bunch of numbers in my set y that I'm never going to use. I'm never going to use any negatives. So the entire set y is not my range. My range is just the numbers in y that I use. If I want to get fancy about it, it is the subset of y. That would be my range. Okay. So see how in this example over here, the range is inside of y. So for our purposes, out here would be all the negative numbers, and in here would be 0 and all the positive numbers. And f would be the absolute value function. Up here, the domain, they can be negative, they can be 0, they can be positive, it doesn't matter. But what happens when you take that absolute value? All the negative numbers change sign, become positive numbers, because the absolute value measures the distance from 0 and all of that. Right. Now, functions can be specified, can be defined, can be given to you in a variety of ways. We usually work with functions that are given by equations involving independent and dependent variables. For example, here's an equation that has independent and dependent variables. And so we would say that x is the independent variable and y is the dependent variable. Right? And that y is defined in terms of the independent variable x. Now, some more terminology, implicit and explicit, or implicitly and explicitly. Okay? An implicit or implicitly defined function is when the function is written and it is not solved for the dependent variable. So I could just simply take this one from up here and do this to it. Oops, that would be a negative x squared, right? Yeah. Now that is no longer, it is still a function, but it is no longer defined explicitly. It is now defined implicitly because the x's and y's are mixed up. Okay. So an explicit or an explicitly defined function is when it is solved for the dependent variable, like that one up there. Okay. And we can then rewrite those using function notation. Now, function notation is also sometimes referred to as Euler's notation. Okay. But it's the idea of replacing the dependent variable with a letter and a set of parentheses. So I could say that g of x is equal to x squared plus 9. Now the advantage to using this notation over that notation is when we evaluate. Because when we evaluate an explicit function solved for the dependent variable, not written in function notation, we lose information. For example, suppose that we wanted to evaluate this function that we're working with here, x squared plus 9, when x was 2. Okay. If I use this notation right here, that's going to give me y equals 2 squared plus 9, and that's 13, so I get y equals 13. But now if I just look at this last statement, I don't know what the function was that I started with because it just says y, and I don't know what the independent variable value was that I started with. I don't know what I used for x. I'd have to go back up into the work and try to figure it out. And if you've ever seen some people's work, it's difficult to follow to figure out where they started. Now, if I do the same thing over here on this one, my first step is going to be to say that g of 2 is equal to 2 squared plus 9, and then I would say that g of 2 is equal to 13. Now the advantage to this notation is, even when I'm done, I still know where I started. I started with the function whose name is g, so I can go back and find that function. And I know what the independent variable value was. I know that the value was 2 for the independent variable. And I know the dependent variable is 13, obviously. So what you should be taking away from this is that as the math gets more complicated, we have a greater need for more precise notation. And back in your Algebra 1 class, saying y equals was good enough because you were doing very uncomplicated algebra. It was, in the big picture, simple equations, simple algebra. We needed simple notation. This is calculus. It's getting more complicated. Because it's more complicated, we need more complicated notation to keep up with the complicated mathematics. Okay? If you had simply just written this as your answer here, I would not accept that, because just simply saying 13 doesn't tell me what function you're working with and what was your independent variable value. So we need to make sure that we define things as they are. This is the function g, this is the function g defined when x is 2, and the value of the dependent variable for this function is 13. For example, here I have a function, f of x equals x squared plus 7. I want to evaluate for each of these expressions. Over here I want to do f of 2. First thing I'll do is I'll show you how not to do it. Don't do this, because that's not right. This is correct. F of 2 equals f of 2 equals f of 2 equals. So now I know that it was the function f defined when x is 2 and its value is 11. So f of 4a, 4a squared plus 7, 16a squared plus 7. So f of 4a is 16a squared plus 7. I can't simplify it any further because I have two terms. One is a constant, 7, and the other is a variable term on the variable a. So they can't be combined. Last one over here on the right, f of x plus 2. And so we have f of x plus 2 is going to be equal to x plus 2 squared plus 7. X plus 2 squared is x squared plus 4x plus 4 plus 7. And so then, combining the like terms that I can combine, I get x squared plus 4x plus 11. And so in each of these examples, the final answer is going to contain the definition of the function, its name is f, a definition of the independent variable value, whether it be the 2, the 4a, or the x plus 2, and then the value that the function is equal to or evaluated at under that independent variable value. Right? All right, that's about 15 minutes right there. So I'm going to stop this video. We'll come back in part 2. And in part 2, we'll start down here with domain and range of a function. I'll see you all back here for part 2.